Professor Arun Kumar Shandilya, Department of Applied Geology, Dr. Harisingh Gaur, Vishwavidyalaya Sagar. Hello dear friends, I welcome you in these programs, and today I am going to talk on the applications of stereographic projections. The stereographic projections are equal area stereographic net. There are two different types of the stereographic nets are Wolf equal area stereographic net, which is used in crystallography, and another one is Schmidt's equal area stereographic net, which is used in the structural geology. In the structural geology, the Schmidt's equal area stereographic nets are mostly used for the plotting of the various data which has been collected from the field of the different structures, bedding planes, joints, and foliations and lineations, and the faults and the fold axis all are plotted on the stereographic net. And on this stereographic net, we must have the data related with the dip of the bedding plane, dip of the limb, dip directions, and the strike directions. If we have the minimum these three data, then we can plot them on the stereographic net. And on the stereographic net, we had to plot the directions on the periphery of the projections 0 to 360 degrees is it given in the stereographic net, and the bedding planes are plotted on the east-west line, which is given in the projection stereographic net. The amount of dip etc. is plotted on the east-west line. So, the point which we are measuring, see the example is the strike is north 30 degree, amount of dip is 40 degree, and direction is towards 120 degree. So, what we will do it, we will mark north 30 degree on the stereo net and on the periphery of the stereographic projections, and then we will rotate it, take it to the north points on the north south line, and then from the east right hand side or from the east direction we will count the amount of dip, and this point will be called beta pole. And when we will draw the girdle from north point to south point, then it is called as a girdle. It is a smooth curved line is called girdle, and a straight line is called the plane. So, we are simply plotting the plane, or we can say we are plotting the bedding plane or the limb of the bed, right. So, this is a simple method of plotting the structural data, either the bedding plane or the limb dip of the limb of the fold. This we can plot it. If we have the number of data related to the bedding plane as well as the limb of the folded strata, we can easily plot the data. We have to do the measurement in the field, we have to collect the data from the field, and then we have to utilize the stereo net and we have to plot them. So, the application of this stereo net is we can we can plot the bedding plane. As I told you that the applications of Schmidt's equal area stereographic nets, we can plot the bedding plane as a simple plane in the stereographic projections. With the help of the Schmidt's equal area stereographic net, we can plot the dip of the limb of the fold, number of limbs we can plot on it, and wherever these all girdles are intersecting, that point is called the plunge of the fold. That we can rotate it, bring it this projection on the north south line, and we can do the measurement of the plunge amount, how much the fold is plunging. So, the plunge of the fold can be determined with the help of the Schmidt's equal area nets, the data which we are collecting from the field, and it is utilized in the Schmidt's equal area stereographic net. Then we will bring the stereo net or the tracing paper on the stereo net its original positions, matching the north of the tracing sheet with the north of the stereo net, and we can easily find out the direction of the plunge. So, the amount of plunge and the direction of plunge we can directly measure from the stereo net. So, this is one of the applications of the stereo net. Then we can easily find out the true dip. If we have collected the apparent dip from the field 2, 3, 4, 5, 6, whatever the values of the apparent dip we are collecting from the field, we are just plotting this apparent value of the dip on the stereo net, putting the dot. These dots are called beta pole. Now, whatever the number of beta poles are there of the 4 apparent dip, 5 apparent dips, 6 apparent dips or 10 apparent dips, we join them all, we bring all this in a one particular girdle. So, that girdle which is drawn, we can easily directly measure the amount of true dip. So, with the help of apparent dip what we have collected from the field, we can utilize it for determination of true dip of a complicated and very highly deformed terrain. We can find out the true dip of the beds. true dip of the limbs, we can easily find out it. Now, in other applications of the symmetric equal-area net is we can easily find out the apparent dip in the different respective direction, because we can plot the true dip directions on the stereographic net, and in the required direction we can easily find out the apparent dip. This is one part of applications of the symmetric equal-area stereographic net. And then there is another use of this is symmetric equal-area stereographic net is for plotting the joint data. If you have number of more than 200, 500, 1000 joint data are there, then we can use we can plot the joint value, joint dip of the joint plane and strike, and then we just 90-degree opposite to the point of dip of the joints, that point is called pi pole. So, the pi pole diagram can be prepared with the help of the symmetric equal-area nets. Means we are preparing two different diagrams. One diagram is called beta pole diagram, another diagram is called pi pole diagram. Pi pole diagrams are used for the representation of the joint data which we are collecting from the field, and then we are doing on this contouring of the map. So, this applications we can easily utilize the stereographic projections for the structural analysis in the very deformed terrain, the area which has suffered more than 2 generation, 3 generation, 4 generation folds are there, and even if we get the foliations data from the field, lineation data from the field, and the fault data from the field, these all data can be plotted, because the planar structure can be easily plotted. Linear direction can also be plotted on the equal area stereographic nets. What we call it, it is a symmetric equal area stereographic net, and in this map we can easily mark all the data which we are collecting from the field. Say the foliation data means bedding cleavage, axial plane cleavage, slip cleavage, shear cleavage, fracture cleavage, cystosity and necessity. All these data can be marked on the stereographic net, depending upon if we have the sufficient data is available. Means the inclination of the plane, foliation plane's inclination, the amount of dip of the foliation plane, its direction and its strike. If we have this data, we can easily mark on the symmetric equal area stereographic net. Now, so we will give the title to depending upon which type of data we are using for the representation of in the stereographic net. So, we will decide accordingly the name of the figure. Say if we are using the joint data and the pi pole diagram is there, then we will write the name of the figure will be pi pole diagram of the joints. If we are plotting the pi pole diagram of foliations, we will write down pi pole diagram of the foliations. If we are marking the pi poles of various bedding planes, we will write down pi pole diagrams of the bedding planes or the limb of the fold. And if we are marking the fault plane, we can easily mark the throw of the fault, we can mark the thrust of the fault, we can mark the different type of the faults are there. Fault means it is a type of reverse fault. We have the thrust fault, we have the nappe structure, all different type, because they are the planar structures. We can easily measure the inclination with the horizontal surface, that is called the dip of that particular fault plane, and that can be plotted on equal area, symmetric equal area stereographic net, and we can easily find out its various geometrical relationship on the regional scale. Say area suffered the 3 to 4 generation of deformations, we can easily set these directions of different structural features. They are making a center points on the different points on the stereographic nets. Now, in geology, we are using another type of the equal area stereographic net, that is called Wolf equal area stereographic net, and this net is especially used for, because both the stereo net, Schmidt's and Wolf equal area stereographic net, they are the equal area nets, but the Schmidt's equal area net is used in the structural geology, and Wolf equal area stereographic net is used in the crystallography. Crystallography is the subject in which we are studying the morphological character of the crystalline matter. Crystal which is composed of face, edges and solid angle is called the crystal, and the crystals containing the various faces is containing the axis, crystallographic axis, 3 crystallographic axes, 4 crystallographic axes are there, and in this crystallographic axis and these faces where they are intersecting, we are defining out the indices is called Miller indices. Miller indices, then we are finding out the different type of the faces, and these faces we can easily mark on the Wolf equal area stereographic net. Now, on the stereographic net, we are plotting the position of two different crystal faces. I will tell you first what are the different type of the crystal faces. We have in the crystallography, we have the common type of the form. The face meeting only one crystallographic axis is basal pinacoid, another face is side pinacoid, another face is front pinacoid. They are meeting only front to back axis is called front pinacoid, side to the face which is meeting side to side axis is called side pinacoid. In this is not one knot, and the face which is meeting only the C crystallographic axis is called the basal pinacoid. So, these all three faces can be easily marked on Wolf equal-area nets. Now, when we will have to mark the different faces of the crystal, like the faces, like I told you, the common forms, the pinacoids are there, then you have the prism. Prism face is a face which is always parallel to C crystallographic axis, meeting maybe at one crystallographic horizontal axis or the two horizontal crystallographic axis at an equal distance or at an unequal distance. Those faces are called the prism faces, right? And then the different type of the prisms are there in the tetragonal system and hexagonal system. We have the tetragonal prism of first order, second order and third order. Then in the case of hexagonal system, we have the prism for first order, second order and third order, but in orthonormic system, we are having only one set of the prism is there, right. So, different prism faces are marked on the periphery of the stereographic projections. Only on the periphery of the stereographic projection, we are marking them on the depending upon what the angle between the two adjoining faces, the normal drawn on the two adjoining faces, and the angle which we are measuring is called interfacial angle. And this interfacial angle is very important for the use of Wolf equal-area stereographic net. With the help of the interfacial angle, we can plot all the crystal forms, whatever available in the crystals. We have to do the measurement of interfacial angle. Interfacial angle, and we can plot, we have measured the angle between which phase, whether it is a prism face and the pinacoidal face, prism face and the pyramidal face, prism face and the dome face, whatever the relationship between the two adjoining faces. So, with respect to that particular face, we can easily mark the position on the stereographic net, depending upon what the angle it is, interlimb angle is there. Depending upon the interlimb angle, we can easily mark the different respective faces on stereographic projections. One projection which is purely used for the crystallographic studies, another projection which is used only for structural study. In the geology subject, both projections, they are having their own importance, because both are using the mathematical data for plotting the crystal faces in the Wolf equal-area net, and the structural, we are collecting the data from the field in the deformed terrain, various type of the bending plane, fold limb of the dip of the limb of the fold, plunge of the fold axis, and the foliations, fault plane, lineation, joints, all different data which we are collecting from the field. It all data are generally plotted on Schmidt's equal-area nets. Wolf equal-area nets, we are using it for plotting of the crystallographic data, crystal faces. Symmetry of the crystallographic axis can also be marked on the projections, Wolf equal-area projection. The plane of symmetries, the axis of symmetry, the type of symmetries are there, three different types of the symmetries are there, plane of symmetry, axis of symmetry, and center of symmetry. All these three symmetries can be marked on the stereographic projections. Now, in the horizontal plane is marked in the circle of the stereographic projections, and a vertical line on the stereographic projection is representing AC plane, and horizontal line in the stereographic projection representing the B axis, containing the B axis and C crystallographic axis. So, the three plane we can easily mark on the stereographic projection. These are called the crystallographic plane or principal plane of symmetry in the crystals. Say in the example, all the crystal systems, cubic system having the three principal plane, tetragonal system having three principal plane, hexagonal system having four principal plane, and orthonormic system having the three principal planes. So, all three principal plane can be marked on the stereo net. The vertical line is representing front to back axis, horizontal line representing side to side axis. Vertical line is the A axis. On the right hand side, we can mark the B axis, and the intersection of both the points is called the C point, or the axis of C point. So, these three axes can be easily marked, and the principal plane can easily be marked on the Wolf equal-area net. Now, depending upon the secondary plane, principal plane which containing minimum two crystallographic axes. Principal plane is a plane which containing minimum 2 crystallographic axes, and the secondary plane is a plane which is oblique to any of the crystallographic axes. It containing one crystallographic axis and it is oblique to another crystallographic axis. So this angle is called the angle between the principal plane and secondary planes. Say the basal penoidal plane and the prism face. So whatever that angle comes, that angle have to be marked on stereographic projections. In the Wolf equilaria stereographic net, we can mark the vertical line in the stereographic net, vertical line as a axis, horizontal line as a b axis, and wherever this horizontal and vertical line intersecting on the stereonet, that point is called indicating the c crystallographic axis. So all these 3 points, the periphery, the plane which is containing both the horizontal crystallographic axis a and b axis, can be marked on the periphery of the projections. The vertical line which containing periphery which containing the circle is containing the a axis and b axis, vertical line containing a axis and c axis, horizontal line is containing b axis and the c axis. So the 3 principal plane we can easily mark on stereographic projections. The secondary plane, depending upon the angle between angle with the crystallographic axis, that plane is intersecting at what angle? Say the 45 angle, we will mark at a 45-degree angle the secondary planes. Say in the case of isometric system normal class, it is having normal class Galilean type, it is having 9 plane of symmetry, 3 principal plane and 6 secondary planes. 3 principal plane which I already told you, plane number 1, 2 and 3, the vertical line, horizontal line and the periphery, they are representing 3 principal planes. The 6 secondary planes they are marked on the Wolf equilateral net at an angle of 45 degree, both on the horizontal line as well as the vertical line, and they are coming in the cross also. So total 6 planes can be marked on the stereographic net. This is the maximum in the crystallography, because the normal class of the cubic system is having the maximum number of the crystal faces found in the crystallography, maximum number of plane of symmetry, maximum number of axes of symmetries are also present in the normal class Galilean type of the cubic system. So I told you how we are going to mark the axis of axial character, how we are going to mark the plane of symmetry. Now I am going to tell you how we are going to mark the axis of symmetry. In the axis of symmetry, in the normal class of the cubic system, we have 13 axes of symmetry, 4 axes of 3-fold symmetry, 6 axes of 2-fold symmetry and 3 axes of 4-fold symmetry. 3 axes of 4-fold symmetry is a original crystallographic axis. When we hold the crystal through crystallographic axis, rotate it will give the axis of 4-fold symmetry. All the 3 crystallographic axes, they give the axis of 4-fold symmetry. So we write it as a 3A4. Now when we are holding the crystal through the solid angles of the cube, when we are holding and rotating it at an angle of 120 degree, when repeating the complete 360 degree, it is giving the axis of 3-fold symmetry. We write it as a axis of 3-fold symmetry. So all cube containing the 8 solid angle, 4 solid angle on the top side, 4 solid angle on the bottom side. So total 8 solid angle are there. A pair of solid angles give the axis of 3-fold symmetry. So it will give the 4 axis of 3-fold symmetry. First we hold the crystal through the center of the faces, then second we hold crystal through solid angles. Now we are holding the crystal through edges. Edges means where the 2 faces are meeting. Edges means it is where the 2 faces are meeting, the straight line is called the edges. When we are holding the crystal through edges, it gives the axis of 2-fold symmetry. See, a very ideal crystal of Galilean, which composed of 6 faces, 8 solid angles and 12 edges. I already told you when we are holding the crystal through the face, center of the face, rotating it at the interval of 90 degree, it gives the axis of 4-fold symmetry. The same face is repeated 4 times. So we call it is the axis of 4-fold symmetry. So the pair of the faces will give the axis of 4-fold symmetry. There are 6 faces are there. So it will give the 3 axis of 4-fold symmetry. Now after the face I am coming to the solid angles. Solid angle of the cube face, 4 solid angle on the top side, 4 solid angle on the bottom side. So total set of 8 solid angles are there. So a pair of solid angle, it gives the opposite end pair. Opposite end solid angle gives the axis of 3-fold symmetry. Means when we are holding the crystal through solid angles, rotating it the interval of 120 degree, it gives the same face as repeated, same solid angle as repeated, or same edge has been repeated. And during your 360-degree rotation, same edge, same phase, same solid angle is repeated 3 times. So, we will call it as the axis of threefold symmetry. So, as I told you, the crystal made up of the face, edges and solid angle. We have used faces and we have used the solid angle. What remains, remaining part is edges. What is edge? Edge is a contact point of the two faces, two adjoining faces, and this straight line is called the edge. Now, when we are holding the crystal from the two opposite end edges, rotating it at the interval of 180 degree, same face, same solid angle or same edge is repeated 2 times at the interval of 180 degrees. So, this edge will give the axis of twofold symmetry. In the crystal of cube, there are 12 edges are 4 on the top side, 4 vertical and 4 on the bottom side. So, total number of edges is 12. So, the 12 edges will give the axis of 6-pole symmetry. So, we can easily mark the 6-pole symmetry axis with a symbol. We call it biconvex symbol, a cube face and the triangle, equilateral triangle is used for demarcating the axis of symmetry in normal class of the cubic systems. So, 3 different symbols are used. In the same stereographic projection tracing paper, we will mark the plane of symmetry and then we will mark the different axes. Where we have marked the A axis, B axis and C axis, we can mark the symbol of cube at the A axis point, negative end, positive end, B axis at the positive and negative end, and the C axis or the A3 axis as a cube face. So, cube will be marked on the 3 axis point. Then we will mark axis of threefold symmetry axis, we will mark the axis of two-pole symmetry. So, this way we can easily mark all the different faces are can be plotted on Wolf equal-area stereographic net. Now, in the normal class of system, normal class of the isometric system, we have the cube form, we have the tetrahexahedron, we have octahedron form, we have the rhombododecahedron, we have the trisoctahedron, we have trapezohedron and hexaoctahedron. So, the hexaoctahedron form is having 48 number of faces. This all 48 faces can be plotted on stereographic net. Trapezohedron and trisoctahedron both are having 24 number of faces. If we have the sufficient data of interfacial angle between the two adjoining faces, if we have the sufficient data, we can mark all the 24 faces of trapezohedron and trisoctahedron on the stereographic net. The 8 faces of octahedron can be easily marked. 8 faces, because all face meeting all the 3 crystallographic axes at an equal distance, it can be marked on the Wolf area stereographic net. Now, the another face, rhombododecaedron, the face which meeting the 2 crystallographic axes at an equal distance and parallel to the 3rd crystallographic axis. So, that can be marked on the respective points depending upon what the angle between the cube face and dodecahedron face is, say, 45 degree. The angle between interfacial angle between a cube face and the rhombododecaedron face is 45 degrees. So, wherever the 45 degree point we will get in the stereographic projection, we will mark all the 12 faces of rhombododecaedron in the stereographic projections. Now, see, one projection is used purely for structural geology, one projection is stereographic net is used for the crystallography. I told you the crystallography applications of Wolf equal-area stereographic net for the crystallography part and the symmetric equal-area stereographic net which can be used for structural data. Both analysis is very helpful in the geological study. Crystallization, the data related to the crystallization is used for we are using the Wolf equal-area net, and all the deformation phases, 2 generation deformation, 1 generation deformation, 2 generation deformation, 3 generation deformation, 4 generation deformation, all the deformation is resulted in the form of different type of the folds, different type of the joints, foliation, lineation, and fault. So, that can be plotted on the symmetric equal-area stereographic net. Now, with these applications of this stereographic projection, we can analyze the number of data, whatever the data is already available, or students who goes field and collect number of data from the field and they can analyze in the laboratory. See, in the geology subjects, we are using 2 different type of the equal-area stereographic projections, or we call it the stereo nets. In structural geology, we are using the symmetric equal-area stereographic net. In the crystallography, in which we are utilizing the equal area stereographic net is discovered by or is given by the Wolf. So, we call it the Wolf equal area stereographic net. In the Wolf equal area stereographic net, we are measuring the different crystal faces, crystallographic character of the crystal faces we are plotting on the Wolf equal area net, and whatever the data we are collecting from the deformed terrain, which may have first generation, second generation, third generation deformation has occurred in that area. We can go, or the student can go in the field and collect the different data pertaining to dip strike, dip of the limbs, lineation, foliation, fault, joint, all number of data he can go and collect from the field, and then he can plot it on the CIMET's equal area nets. And he can interpret it, what is the tectonic history of that particular area, because with the help of this stereographic projection data and the result, we can predict the deformation phases of that particular area. Means we can conclude it that by the plotting of the different structural dot and the CIMET equal area nets, we can come to know what are the different type of the deformation occurred in that particular area. Okay, dear. Thank you very much.